In this video, we'll do a conformational analysis of some of the acyclic alkane where we will calculate their actual energy and analyze them very carefully to determine which of the conformation will then be more stable. So let's get started with first ethane. Now in ethane, we have seen already that it has two possible conformations, the stacker and the eclipse. And here are some of the views, especially the Newman projections, that we'll pay attention to. So in this stacker conformation again, stacker refer to the fact that the group are not eclipsing each other, where they do not line exactly on top of each other, but then they tilted in the middle between the two groups. Versus in the eclipse, then this is where the bonds or the groups from the two adjacent carbon are basically exactly overlapping on top of each other. Just like the eclipse moon when it's covered the sun. So in this case, one is covering the other, and that would then be the eclipsing conformation. So these are the two possible conformations of ethane. Let's now calculate their energy, and let's look at some of the statistics about them. So first one, the dihedral angle. So the dihedral angle refers to the bond angle between these two groups right here in the stacker conformation. And in this case, this will then be 60 degrees. And for the distance between these two hydrogen right here, it has been found to be 2.44 angstrom. Now, when we compare that with the eclipsing conformation, then again, the two hydrogen are basically overlapping on top of each other. So the dihedral angle between these two hydrogen would then be 0 degree angle, 0 degree. And as for the distance between the two hydrogen, they will now be closer, right? So in this case right here, this has been found to be 2.29 of angstrom, which is then basically closer compared to the distance between the two hydrogens seen in this eclipsing conformation right here. And now, because this hydrogen right here are very close to each other, they then have steric energy to them. And each of this eclipsing hydrogen right here, so each eclipse hydrogen between two hydrogen equal to 1 kilocal per mole. That's the steric energy that they would have. And in this case, we have three sets of hydrogen that are eclipsing each other. So multiply by 3 total overall. Then this conformation right here, we have 3 kilocal per mole. And this is basically the destabilizing energy. The higher this destabilizing energy, the more unstable it will be. So destabilizing energy. Then the higher it is, then it means less stable. And this value right here, 1 kilocal per mole, this is set relative to the other conformation that would have none. So in this case right here, in the stacker conformation, there would be 0 kilocal per mole. And relative to this 0, this will then have 1 kilocal per mole for each of the sets of equivalent of eclipsing hydrogen. So we will then see in this case right here, this will then be the less stable conformation. And this will then be the more stable conformation by about 3 kilocal per mole between the two conformations. And now, let's now do conformational analysis of butane. So in butane, we will have 4 conformations that are different, that are possible. 2 of them are stacker. And then 2 of them are eclipse. And here they are. So here are the 2 stacker conformation. And again, they do not line on top of each other, but then tilted. And they can be tilted in which that the 2 CH3 group are 60 degrees from each other. Or when they're 180 degrees from each other. So this is basically the anti-conformation right here. So the term anti refers to the fact that again, the 2 CH3 group are opposite of each other and therefore anti. So in this case right here, when the 2 groups that are on the 2 adjacent carbon are 60 degrees from each other, this is again called the Gauss conformation. So please remember this term right here, the Gauss conformation, refers to the two groups on the two adjacent carbon that are 60 degrees from each other. And so here will be the energy associated. When these two CH3 group right here, they are a big group, but because they're not eclipsing each other and there's 60 degrees between them, so they do possess some destabilizing energy, and the amount of energy associated in them will then be 0.9 kilocal per mole. So overall, we have these two CH3 groups that are Gauss to each other, and that would then be the total destabilizing energy. So ED stands for destabilizing energy of this conformation, and in this case 0.9 kilocal per mole. The hydrogen do not have any static energy associated unless they are basically eclipsing each other. So in this case, this would then equal to 0. And overall, we only have these two hydrogen that are Gauss with respect to each other, giving rise to that 0.9 kilocal per mole. And in comparison, the NG conformation, so this is set equal to 0 kilocal per mole. Because the two methyl group, they're too far away from each other, so they do not interact with each other. And the interaction between the methyl and the hydrogen, this is also equal to 0 as well. And the reason is because we cannot avoid that. That exists in all of the conformations. So that's why we set that equal to 0. And now moving on to the eclipsants, the two eclipsant conformation. We're going to have the two eclipsant conformation where the two CH3 group are eclipsing each other, or when the CH3 group and the hydrogen are eclipsing each other. And these are the two conformations right here. So this conformation again is called the total eclipse conformation. And now let's calculate how much energy associated when the two methyl groups are eclipsing each other, because they are very big and right now they're overlapping exactly on top of each other. This has an energy equal to 3.4 kilocal per mole. So overall, we see in this eclipse conformation right here that, and again in this total eclipse, we have two methyl group eclipsing each other and two sets of hydrogen that are eclipsing each other as well. So when we add all of this together, it equal to the following. Now again, each of this is then 1 kilocal per mole. So when we add all of this together, this would then equal to, so we will have two sets. So we have 2, and each of this is then 1 kilocal per mole. And this is for the eclipsing hydrogen. Plus, when the two methyl groups are eclipsing each other, is 3.4 kilocal per mole. And we have one of that. So added all together, this equal to 5.4 kilocal per mole altogether for this total eclipse conformation. And the other eclipse conformation will be as follows. So here in this case, the methyl and the hydrogen are eclipsing each other. And because the methyl is bigger than the hydrogen, then this would also produce static energy as well. And in fact, each of this would then equal to 1.4 kilocal per mole. And we have 2 of that. And we also have the 2 hydrogen eclipsing each other, and this is 1 kilocal per mole. So when we add all of this together, the total destabilizing energy for this eclipsing conformation would then equal to 1.4 kilocal for the eclipsing hydrogen and the CH3 group. And we have 2 of this, plus the 1.0 kilocal per mole for the eclipsing hydrogen. Adding together, this equal to 3.8 kilocal per mole. So this are basically the relative destabilizing energy of the 4 different conformations that is seen in butane. And we will then see that the anti-conformation is the most stable one, followed by the God's conformation. And at the total eclipse, this have the highest destabilizing energy right here.